In this video, I'm going to solve some word problems involving marginal analysis. The technique that we'll be using is the antiderivative because we're going to be dealing with problems where the marginal function is given and we have to recover the original function. So here's an example. Suppose we're given that the marginal revenue function for a business is r prime of x equals 94 minus 0.06x, and that's when the business produces and sells X units of its product. What is the revenue function? Okay, well, take a moment, pause the video, try to solve this. Okay, well, here's that marginal revenue function again. Incidentally, you have to remember that, okay, R revenue is total money collected from sales R prime is the marginal revenue function, and that's equal to the derivative of R with respect to number of units sold. In the past, we've been given examples where we have a revenue function or we construct a revenue function, and then we take the derivative to get the marginal revenue function. And then maybe we use that to, say, find a critical point and optimize the revenue. But for this problem, we're going backwards through that. We're given a marginal revenue function, and we're asked to reconstruct the original revenue function that it must have come from. Okay, well, what we need is to go from R prime back to R. So to go from R prime back to R, we need an antiderivative. I'll use indefinite integral notation. So big R of x should be the indefinite integral of R prime, and we're going to take the integral with respect to x because that's our independent variable. Okay, remember that we have an antiderivative power rule. Which is that the antiderivative of x to the m dx is, do you remember what this is? Yep, 1 over m plus 1 times x to the m plus 1. And depending on the circumstances, you might see that written with the plus c, or the plus c might be left out of the formula, and you just have to know to put it in. Well, in order to use that here, I've kind of gotten ahead of myself. We have to deal with the subtraction first. So for that, I'm going to remember that the antiderivative of a left minus a right is that we do the antiderivative of the left minus the antiderivative of the right. In each case, we have a constant that's multiplying, well, sort of multiplying something. Here we have just the integral of a constant. We've done examples of this before. This is perhaps so easy it's hard. This is with m equal to 0. So the antiderivative of just 94, and keep in mind this is the antiderivative of 94, 94x. minus, now we need to handle this other piece. Remember, we keep multiplication by a constant when we're doing an antiderivative. That's because you keep multiplication by a constant when you do a derivative. So far we have r of x equals 94x minus 0.06. And then the antiderivative of x will be done with this antiderivative power rule. If it helps, x is x to the 1. The antiderivative of x to the 1 is 1/2 x squared. And finally, I'll add a constant. In business problems, I usually use k for the constant because most of the time c looks like a cost function, and just to avoid confusion, I'll use k for the constant. So now we can clean this up. R of x is 94x minus, and well, we may as well do that arithmetic. Half of 0.06 is 0.03, so 0.03x squared plus k. Now, we really need to figure out what to use for k. Here's where you have to go back to the definition of revenue. I wrote it down up here. The revenue function is the total money collected from sales. Well, we have a piece of information about revenue that you may not remember. If we sell no units, we collect no revenue. So we collect 0 revenue. In other words, even though I haven't been given this information in the problem, you have to understand from the definition of revenue that R of 0 is 0. If we sell no units, we collect 0 revenue. Well, let's fill that in, right? R of 0 is 94 times 0 minus 0.03 times 0 squared plus k. Well, R of 0 is supposed to be 0, and well, all of this is 0 and all of that becomes 0, so we're left with just k. So that means the constant of integration is 0. So then the final revenue formula, final revenue function, is just R of x equals, and I'll just write this again, but fill in k equals 0. So 94x minus 0.03 x squared. And this is the thing that you would type into Hawks, for example, to put in for your final answer. To check this, clear that out. Well, you can just take the derivative. We'll go back from r to r prime. Well, what is r prime of x? From here, 94 minus 0.06x. And since that matches the given information, that means that we've done our antiderivative right and we've done our derivative right. So this is good. One more thing. Remember that usually we think of revenue, not every problem works this way, but we can do number sold times price. So that means that we're usually working with R of x equals x times d of x. We were not given a d of x, a demand function, in this problem. But if you look at this function, r of x equals 94x minus 0.03x squared, you can factor out an x, and that will leave you with r of x equals x times 94 minus 0.03x. And so even though the problem didn't ask about it, you can do this calculation and figure that this must be d of x. So just a little bit different way of looking at marginal revenue. Okay, and again, what this problem was asking for was the revenue function, and that's the answer that we're asked to compute. So let's do the next problem. This problem says the marginal cost function for a business is c prime of x equals 20 plus 0.01x, where x is the number of units of its product. The fixed cost is $1,500. What is the cost function? Okay, so take a moment and try to solve this problem. Okay, let's get into this and see what we can do. Okay. Well, first, we're given the marginal cost function, and we need to recover the cost function. Well, since the marginal cost function is c prime, the derivative of cost, we need an antiderivative. Okay, so c of x should be the antiderivative of c prime. So I'll set that up. So there you go, c of x is the antiderivative of c prime, the indefinite integral of 20 plus 0.01x. And we're going to integrate with respect to x because that's the independent variable in this problem. We've done a few of these, so I'm going to assume that you don't need to see all of the steps. Let's first deal with the 20, and then we'll deal with the 0.01x, and we can do that because we're just doing the antiderivative of the sum of these terms. Okay, antiderivative of 20 is $20x. Okay, then we will add the antiderivative of 0.01x. We keep multiplication by 0.01, and then the antiderivative of x is 1/2 x squared. Then we need to put in a constant of integration. And again, since this is a business scenario and we've used big C for the cost function, I'll use K for the constant of integration. Okay. When you clean this up a little bit, you'll have 20x plus, this should be 0.005 x squared plus K. How are we going to find K? Well, we've been told that the fixed cost for this business is $1,500. Now remember how cost works. C of x is total cost to produce x units of whatever product this business is making. And remember how C of x can be thought of as fixed costs plus variable costs. The fixed costs don't depend on x. These are things like rent and maybe insurance that you have to pay the same amount for no matter how many units of your product you produce. And the variable costs, those are all the terms that do depend on X. And an important thing to know is that C of 0, that says that we make nothing but still tabulate the costs as possible. C of 0 is just the fixed cost component, because if we're making no units, there's 0 variable costs. So this information that the fixed cost for this business is $1,500, that's telling us that C of 0 is 1,500. Okay? So again, the fixed cost information is telling us C of 0. So fixed cost is $1,500 means C of 0 equals 1,500. So let's fill that in. On the one hand, C of 0 should be 20 times 0 plus 0.005 times 0 squared plus k, but C of 0 is also equal to 1,500. When we simplify stuff over here, all of this has multiplication by 0 in it, so that goes away. The next one has multiplication by 0, so that goes away. So that leaves us with just 0 plus k equals 15. So in other words, 1,500. K is 1,500. That's the last piece of information we need to write down the total cost function. So the final cost function is C of x equals 20x plus 0.005 x squared plus 1,500. Again, you could check this by taking the derivative. That should return you to the equation for C prime that we started with. And you can also check that C of 0 is 1,500. That's actually very easy to do because this is a polynomial in expanded form. It's very easy to plug in x equals 0. Okay, so that's an example of recovering the cost function for a business from its marginal cost function. Now you may be wondering, why would anyone ever have the marginal cost function, but not the cost function? Well, here's an example of that. This problem has the sort of peculiar feature that it's easier to write down the marginal cost function than it is to write down the total cost function. So here's how we do this. A distributor buys bleach from a factory for 25 cents per liter plus a flat $700 delivery fee, and it arrives in one big shipment of X liters. It costs 2 cents per liter per day to store the bleach. That's rent and maintenance and so on. The distributor then sells the bleach at a rate of 120 liters per day. How much does it cost the distributor to buy and store X liters of bleach until it's all sold? So this is a case where we have to be a little more careful about the inventory costs. Normally, we don't get into a lot of details like this in the problems we've done in this class. But in this case, the costs are sort of an interesting part of the business modeling process. And especially if you're a distributor, one of these intermediate steps in the supply chain, distributor or wholesaler, then most of your costs are going to be things like storage, insurance, maintenance on your storage facilities, transportation, things like that. So figuring out what these storage costs are going to be does end up being important. For a dangerous chemical in particular, the storage costs may actually be significant because you have to have specialized equipment to handle it. Um, you may have to have special licensing. You may have to hire experts in handling dangerous chemicals, things like that. So that's kind of the context of this problem. So let me write down here a little bit about the bleach distributor problem. Now, there's a couple of steps to this that are not easy to come up with. Let me give you a picture of what happens. So here, for example, is our storage tank. We fill it up with bleach, and then at some rate, we bottle it, put it in smaller containers, and ship it out to wholesalers or to someone who uses the bleach in some industrial process, for example. And while it's sitting here in the storage tank, it accumulates costs. Yeah, so this is kind of a peculiar way of thinking, but you need to imagine that we're going to attribute the cost of the facilities to individual liters of bleach. And here's a way to do that. So suppose that there's X liters of bleach in the storage tank. And we're going to imagine this liter here at the very top. We're going to imagine selling the bleach one layer at a time. And we want to know how much cost does that last layer of bleach accumulate. So remember, we are told that there's a cost of $0.02 per liter per day to store bleach. So the cost that this liter up top accumulates before it's sold depends actually on how long it takes to sell all of the liters underneath it. Right? We have to sell all of that before we can sell the one on top. Okay. So to sell X liters ahead of it in the container, how long does that take? How many days does it take to sell X liters of bleach? And remember, here's the problem statement. So the distributor sells the bleach at a rate of 120 liters per day. So that means that in T days, we sell 120 times T liters of bleach. Well, that means that if X liters of bleach are to be sold, then T must be X over 120. So let me go back up here and fill this in. It takes X over 120 days to sell X liters of bleach. Well, what does that buy us? That means that the next liter has to wait around for X over 120 days. Here's where the marginal analysis comes in. If you'll recall, C prime of X is approximately the additional cost to produce and sell one more unit. So if we've got the first x liters under control and we were imagining what would happen if we wanted to, to sell an extra um, unit, C prime of x should be the cost to store one more liter until the first x are sold. And we've just determined that it takes x over 120 days to do that. So x over 120, that's how long. And then remember, we're given this information that there's a cost of 2 cents per liter per day to store the bleach. So while we're waiting for x over 120 days to pass, each one of those days contributes 2 cents. So that is the marginal cost function as far as storage. So this is storage. And that's the hard part of this problem. There's an easier part of this problem that there's a 25 cent per liter per item cost. That's just to acquire the material itself. So to correct, or rather complete C prime, I need to add what? 25 cents. So this is just a material cost. It's 25 cents per liter plus the time it takes to store it times 2 cents per day. And so there you go. We have storage costs and just buying the material. Now, to clean this up a little bit, the problem with these numbers here is that we're about to get a very small number. If you put this into your calculator, the number that I'm about to get is 0.02 over 120, and then I'll keep the x over there as a separate factor. 0.02 divided by 120 is it's like 1.67 times 10 to the minus 4. It turns out that it's going to be easier to deal with the reciprocal of that number, and that is simply 1 over 6,000. That's just an easier number to keep track of. So now we have formulated a marginal cost function. Okay, so again, just to kind of go through quickly what we've done. We've imagined this storage process. We figured out how to attribute costs through the storage. Remember that the marginal cost function is how much extra it costs to acquire, store, and sell one more unit. So there's the plain old material cost that goes into it, then there's this storage cost that goes into it, and at the end of it, what we've got is C prime of x. To get to C of x, which is what the cost function is asking, we need an antiderivative. If C prime of x is this, then plain old C must be the antiderivative of that. So I'll write an indefinite integral of 1 over 6,000 times x plus 0.25. Since this is an antiderivative of a polynomial in expanded form, we can handle one term at a time. Handling this term, we keep the 1 over 6,000 times, And then the antiderivative of x is 1/2 times x squared. So remember, we need the antiderivative power rule here. That handles this first term. Now we can handle the second term. What is the antiderivative of just 0.25? And keep in mind, antiderivative of 0.25, 0.25 times x. Finally, now that we're finished with the antiderivatives of all of these pieces, I'll add in a constant of integration. And since this is a business problem and we've used big C for cost, I'll use K for the constant of integration. Now, looking back at the problem, we need to see if we can find the information necessary to determine what K is. If you look at this problem, there's one piece of information that we haven't arrived yet, that we haven't used yet, and that is the delivery fee. There is a flat $700 delivery fee. So no matter how many liters of bleach we order, it's going to cost us $700 for the truck to come in. That's a fixed cost, and that's the only fixed cost that we have here. So when I come back, the delivery fee is a fixed cost. So that means that C of 0 should be the $700 for the delivery fee. Okay, well, C of 0 is also equal to, you can check this out, 0 plus 0 plus k. When I plug in x equals 0 here, all of that zeroes out, all of that zeroes out, and we're just left with k. So k is 700. Finally, we need to put all of this together. So C of x equals, let me shrink that a little bit. I can do a little bit of cleanup there and multiply the two fractions together. 1 over 6,000 times 1/2 is 1 over 12,000 times x squared plus 0.25x plus, and we just figured out that k is $700. So there we go. And there's the total cost function. Again, to put this in some context, we've dealt with cost functions like this that were just given to us in a problem statement. And I mentioned that terms like this are representative of an efficiency breakdown. When you have a cost function with that kind of quadratic term in it, what it means is that if you're trying to do too much, trying to sell too much, you start running into these problems like you need to have people there for overtime, you have to go to more expensive suppliers for your materials and so forth. Another place where you run into this problem is storage. So that again, if you're storing a bunch of stuff, maybe you have to build a new tank, and you have to figure out how to accommodate that and how to work it into your business business modeling. And it's the kind of thing that can give you these quadratic terms in the cost function. Notice that this coefficient is kind of small. 1 over 12,000 is not a real big number at all. That's that's going to be 10 to the minus fourth. It's going to be around 10 to the minus fourth. So it doesn't come into play unless you're really overtaxing your equipment. But it is something that's worth keeping track of. Okay, so there you go. That's the bleach distributor problem. And again, we had to read the problem carefully. We had to understand what it's telling us as far as how to compute the costs for this business, it actually gave us information about marginal cost, uh, some of which was very easy to interpret and some of which we had to think about. We then had the marginal cost function, but we needed the cost function. That means we needed an antiderivative. So we did an antiderivative of a polynomial. We picked up a constant of integration, and we used the fixed cost, which for this problem was just a delivery fee, um, and figured out what that constant of integration was. And so finally, there's the total cost function.